Our next guest is Birr Pixton. And he works on something really interesting, which probably a lot of you use or depend on, maybe knowingly or unknowingly, because he works on Russell's, or Rust TLS, as I would pronounce it. It is a TLS library in Rust, completely written in Rust. And he spoke at RustNL last year, and he talked about a drop-in replacement for OpenSSL. Now, one thing that I like in particular about your biography is that you say you do like gardening. What is it about gardening that you like?
It doesn't involve any computers.
And with that, take it away.
Thanks. So I can skip over that. I have one point of order before I start my talk, which is some unfinished business from my talk last year. At the end of that, someone asked a really great question, which was, did I find any memory safety problems in OpenSSL while I was doing that work? And the answer was yes, but it wasn't publicly disclosed at that time, so I couldn't really talk about it. But now I can. And so this was a bug which lasted 13 years. It affected basically every OpenSSL version, plus boring SSL. Google paid me a little bounty for that. That was very nice. This line of code here, if you give it to node 9 or before, that will give you a TLS client which leaks up to 255 bytes of its heap to the server when it does the connection, which is really good and normal. But it's not such a disaster. It hasn't, in like half of it, the latter half of its lifetime, it hasn't really been exploitable so much. But quite interestingly, once you kind of know that this bug exists and can cause like crashes and what the crashes look like, you can go and search GitHub and find people. I found one person who was developing the OKHTTP library on Android in 2014, and they're just there in GitHub issues, pasting bits of their heap into an issue saying, why is this happening to me? Why is this happening? So it's in retrospect, and that was before Heartbleed as well. So this was happening in the wild before Heartbleed, which is quite entertaining. I'd also say that like this bug has outlived the enormous amount of money spent on auditing OpenSSL since Heartbleed, which again is like an interesting thing to think about. You know, you can kind of imagine there's some very long tail of vulnerabilities, and I think this is probably at the very long tail in terms of length and how long it has survived in the wild. So, getting onto this talk, I'm going to answer the question very, very quickly, does Rust need more cryptography options? And if the answer is no, then this is a very short talk. And then I'm going to talk about optimizing compilers and their kind of fraught relationship with cryptography code. And then I'm going to talk about this project a bit more. So, does Rust need more cryptography options? I think the answer is yes, but I'm going to try and like motivate that more. And this is just my opinion. It's just an opinion of one person, so take it with as much salt as you like. So I'm going to go through in a few sort of categories like portability, so architectural and operating system portability, build simplicity. So how annoying is it to build as a crate? Performance, and I'm thinking about runtime performance only, not build time performance. And then assurance, which is it's a mix of two things. So a normal cryptography library, I would say, is like 3/4 maths, and it's just like straightforward. I mean, it's complex, but straightforward. And this component of it doesn't tend to have memory safety issues. But then the remainder is parsing some of the worst formats known to man that we've possibly come up with as an industry. So ideally, we'd like that part at least to be memory saved. I don't think I need to argue that any further. So AWS LCRS, this is doing really well at performance and assurance. They've done a huge amount of work on like formal verification of their cryptography. I'm taking off 1 star for like the amount of memory safety going on in some of the parsing code. But yeah, the other thing to say is like, it's quite portable, but for more esoteric platforms, it can be very annoying to build. Very kind of manual, lots of separate dependencies and stuff. And then Ring. So Ring, like the OG Rust crypto library, and kind of made it possible in the first place to write Russells. So I think everyone owes a great deal of gratitude for that project and the amount of work that's gone into it. It's got pretty good performance. It's got pretty good assurance in the sense that memory safety and parsing, and also there's quite a bit of sort of formally verified maths in there as well, which is really good. And now I'm Rust Crypto and Dalek, I'm kind of squishing them into one because that's how they feel to me. They share quite a lot of maintainers, but they've got really good portability and build simplicity because fundamentally they are a vast majority of just pure Rust with some extra options for like using some assembler and stuff. The performance, I would say, varies from world-beating, incredible, to not so good. And the assurance, again, is like varies from really good to not so good. But I think most of these 2 stars is coming from the amount of like memory safe code that is involved here. And then there's this project, and you're probably going, oh God, he's given himself 5 points. What an idiot. But this is coming at the cost of portability, and I'll talk about that later in the talk. So the next thing I'm going to talk about is optimizing compilers. And this is a kind of complex issue, and I'm going to try and make it as simplified as possible. But I don't think I do a super good job. I'm not talking about Rust-C specifically here. I'm talking about basically every optimizing compiler. So GCC and anything using LLVM, and yeah, they all have, to one extent or another, in the past and probably in the future, have these sorts of problems. And the reason is you can't tell the optimizer what our sort of side channel goals are for cryptography, and you're probably going like, what's side channel and what are your goals? So I tried to think of like a really accessible analogy for this and failed, so you're going to have to put up with this. Say you're a spy and you want to have a meeting with other spies, but it's very, very important that no one knows how many spies are in this meeting. And say, just suspend belief for the moment, that you can arrange for everyone to go into a meeting room and not be observed going into the meeting room or coming out. Now, at this point, you've leaked quite a lot of information to someone who can observe the meeting room afterwards. For example, someone can measure like the CO2 in the room afterwards. That would be a good side channel because CO2 sort of declines, I guess linearly with the number of people breathing in the room and the amount of time they were in there. You could like measure the temperature of the seats. So that's another sort of proxy for how many people in the room, assuming people aren't sitting on their laps or moving around all the time. And you can also look at like the size of the meeting room, the capacity of it, because that gives you an upper bound on this like secret value. So these are all like, there's probably other ways, these are all like side channels, if you like, on the number of people who are in the meeting. And that's quite close to how cryptography works, because we have secret values, and then we have kind of quite lossy and noisy ways that those secret values leak to people who are observing the computation. So let's say we've got a function, it does some cryptography, and it's a pure function, it's got inputs and outputs, and then we categorize the inputs and outputs into like secret values that we want to keep secret and everything else. And so, for example, say you're signing an email. The email that you're signing is public, and the signature that you produce is public because you're just about to put them in an email and send them over the public internet, but the private key is secret and you'd like to keep that secret. And then when someone receives it, they do this operation, and you'll notice that there's no secrets involved at all in this. If you know like the root of the word cryptography, you may be like, is this cryptography? Well, it is, because modern cryptography is like largely outgrown like the Roman origin of cryptography, maybe earlier than Roman. Anyway, so the important thing to say here is that this is like completely public. It's a public operation, but we do want like it to be correct. That's the most important thing. And when you're optimizing this sort of code, you don't have to worry about side channels. There are no secrets. So that's a different problem to almost everything else. So now I'm going to add another a sort of third component. I'm calling this a trace because that's what's used in literature a lot. But you can think of this as like a log file of everything the CPU did while computing this function. And so it contains all the instructions, all the memory accesses, but it doesn't contain the data that it was operated on or like the memory contents of the memory accesses, because if it did, then we wouldn't be able to keep a secret for this. So we're not doing this literally. It's like a thought experiment. We're going to give this trace to our adversary and make them as powerful as they can possibly be with like our understanding of how you can observe a CPU executing instructions. So our first goal is basically that there's no data dependency between the contents of the trace and all the secrets, inputs and outputs. And if that's not true, so we basically achieve that by not having any branches on secret data and not doing any memory accesses depending on secret data. But nevertheless, we actually still do need to do these sorts of computations. So like, how does that work? So I'm talking about this table selection idea. So say we've got this table of data, 16 items, doesn't really matter how tall or wide this is. And we want to extract the fifth one, but the fact that it's the fifth one is secret. So we can't just access the fifth index or fourth index here of the array, because that would immediately leak the address, which contains like some multiple of 5 to our trace, and we don't want to do that. So instead what we do is we access every single one of them in any sequence we like, probably just linear, and then we compute a mask for the one we actually want, and then do this. So here we're basically doing the same operation irrespective of the value of the one that we want, and that fulfills our goals basically for the first goal. But we've got a second goal, and this is just really annoying. There are some CPU instructions which are just not, we don't want to use them for cryptography, especially division. Nonetheless, a couple of years ago we had new cryptography, post-quantum cryptography, like brand new stuff, a reference implementation which used division. So this goal is, I think, shared generally by cryptography people, but is still not amazingly adhered to, shall I say. The other thing on ARM, we've got this really interesting DIT bit where you basically tell the CPU, I'm executing cryptography, please do your very best to make sure that you do not screw me when it comes to this goal and the previous one. So that's a summary of where what the goals are when talking about side channels. And we did have a way, a sort of proposed improvement for this for RC. It came out of a workshop in New York in 2020. And that's very interesting and, like, I would say, not reflected in any other high-level languages. Just like the very idea of even doing this. I mean, it didn't happen, but the reason it didn't happen is because I think no other languages are really interested in doing this, and it would require quite a lot of work on the behalf of LLVM. And I guess at the time, and probably maybe now as well, that work in LLVM would be kind of very specific to a feature that only Rust was interested in. So what we did get on that RFC was some really good, like a huge, well, if you've ever read an RFC, I'm repeating myself because like everything's huge, but Peter Schwaber here is a really well-respected, like internationally respected cryptographer. And if you have a phone or a laptop that you've updated in the past year to 6 months, you are running algorithms that he has worked on. And he effectively says, like, if you're doing anything more high level than assembly, you are going to be bitten at some point by your compiler. And how's that going? Well, it's not going super well. So the sort of conclusion there is assembly is probably the right language for high assurance cryptography. And that moves us on to the next point. So there's this really good and interesting project called S2M Big Num that came out of AWS, and it's formally verified cryptography, quite low-level routines in ARM64 and 64-bit Intel assembly. And the formally verified bit is quite important because this is a very low-level language, and so we want to be sure that it's like correct. But also, this is firmly in like the 75% of your cryptography library, which is doing hard maths that needs to be fast. And there's an entire like class of correctness bugs, which I'm not going to say endemic. They were endemic. They have been a problem over a long period of time. And the best idea that we have for addressing those is formal verification. So to give you an example what formal verification means, say you've got a function which adds two numbers. Formal verification basically proves that that function adds two numbers. It doesn't add two numbers and then 1 in 2 to the 64 times gets it wrong and adds an extra bit. And this is basically what this bug in Golang was. And it was massively, well, it was really interesting in the sense it was exploitable. And you could like leak key material through this 1-bit error with very, very low probability. So normal software testing won't find you this bug usually. The tool we have is formal verification for that. Now, using assembly from Rust, you may think, oh, this is going to be a trivial part, but actually I'm making a right meal of this. So the traditional thing is just to give it to a CPU processor and an assembler, and then link it into the final crate. I'm not going to cover this a lot because it's not what I'm doing, and it's also like doesn't address my goals for making this crate easy to build. So specifically, like Windows users have a real problem with like installing an assembler. And that's fine. Not a problem for Windows users. Maybe it's a problem for Windows. So instead, what we're doing is like at development time, converting the assembler to Rust containing inline assembly. And you may think, oh, well, that sounds quite easy as well. And it actually kind of is. It is working pretty well. And we get some nice things, like we don't have to worry about symbol mangling and function entry and exit ABIs and all this stuff. It's the compiler takes quite a lot of this very uninteresting work away for us, and that's great. Oh, and the converter is built in Python. Please don't hate me. So what does it look like? So this like I said, the assembler is kind of a mix of some assembly macros, but mostly C preprocessor macros to do like give things names and repeat bits of code. And that's what this looks like. So this is not an amazing advert for Rust macros, but I think it gets better. We've got lots and lots of macros in the crate as a result, but they're all like auto-generated through this process. We've also got like in the input code, there are some C preprocessor function-like macros, and these expand quite nicely. I think this is actually pretty reasonably readable. Maybe that's a problem with my brain. The other thing is we can, like I said, we can throw away all the ABI handling that the original code contains because the Rust compiler is doing that for us. So this is just a general overview of what like the input and output looks like. I'm doing my very best here to make the output recognizably the same as the input, just for readability, because there's a lot of comments in the input, and I'd really like to keep those and respect the amount of work that's gone into those. This whole process isn't automated completely, so you still have to write some Rust, like the function introduction here, and how to take the Rust types and convert them into the values that the assembly expects. But actually, I think this is really not very awful, and it's quite limited. So now we're getting on to like the actual point of this talk, which is to introduce this library. So the goals really are for it to be like really easy and fast to build. And I obviously want to use make it easy to use with Russells. And so that means targeting cryptography used in TLS. Competitive performance, I think, is very important too, because it's quite easy to make a slow cryptography library. And also licenses. I didn't talk about licenses, but actually this whole project came from last year. I had some conversations with people, and one of the common points was around the sort of vestigial OpenSSL license in some of these projects. Now, I would say that Ring earlier this year has fixed that, so that's really great. But nevertheless, like it being under a permissive license is quite important to me. So where are we at with that? So very like minimal build requirements, around 1 second build time. That's just on 2 laptops I use for development. This is not like a commitment, and it will probably change over time. 2 dependencies only, which you probably have in your dependency tree anyway. And 99.7% line coverage. So there's some work to do there. And that's not a joke, because like I said, all the maths is very like top to bottom. You execute all the code or none of it. This is the features that are implemented. This is basically what gets you off the ground to do TLS with the vast majority of servers on or clients on the internet. And to split these in 2, so the public key parts at the top are all backed by S2M Bignum, and the ones at the bottom are all like new Rust code using intrinsics for performance. And then portability. So as a result of the S2M Bignum thing, basically just targeting the 2 most common architectures, probably for the foreseeable future, although I'm thinking about like how to move away from that should it become necessary. And again, like widely used cryptography only. I'm not going to start like broadening significantly the scope of this crate. That's kind of how to use it. It's quite quite kind of boring, but just to say that there's a Graviola crate, there's a Russell's Graviola crate, which uses Graviola and expresses it in terms of a Russell's crypto provider, which is the abstraction we have for replacing all the cryptography in Russell's. So performance, this is like, there's a suite of benchmarks, and this is a result from those ordered left to right, fastest to slowest. Also, you'll notice in here Golang is there. I have a great deal of love and admiration for the Golang standard library. So I've included that here because that's like a really good, and I think one of my goals is to be as good as that. But you can see that the performance is pretty good. So this is signing for TLS servers, signature verification important for TLS clients, key exchange, which is important for absolutely everything, and then bulk encryption. So this is not so good. I would really like to be able to use ABX512 intrinsics in stable Rust, but I know that is coming. I would love to contribute to what I can. If anyone's doing that stuff, then please come and talk to me. And there's some more stuff on that page, the other architecture and like what versions I tested and stuff. So in the future, well, RSA key generation, I actually shipped that last week. MLChem is another kind of thing which quite recently, like in the last year, has become a necessity for really doing TLS on the internet. So I'm going to work on that. I'm probably going to take a dependency on it because there's a really good crate, which is formally verified, really good performance, and I don't really think I can actually add anything to that. So I'll probably take a dependency on that at the Russell's Graviola level. And then I'll probably think about other architectures, try and come up with an even more demented way of addressing that. So yeah, that's kind of summary. I would say like give it a go. It comes with a general like. You should have a little bit of concern about adopting a new cryptography library. I think this is good, and you should, listen to your body. But I think I would really appreciate like any early feedback, like how it works for you. So yeah, thanks.
All right, Joe, thanks so much for the talk. It was amazing. We have some time for questions, so raise your hand if you have any question. Yes, we see one here.
Hello? Yay, nice. Man, I'm so glad this talk exists because like once every 5 years I have a chance to in Chile to hear someone as good as you. Thank you so much for it. Okay, I have a couple of questions, but this is the one I want the most, I think. So it's a bit long, but how do you cope, and how could one cope with the daunting task that is to implement a cryptography algorithm? Because the math is kind of like paperwork, right? It's not exactly impossible. And I'm only being half facetious here. Just have to put in the time and effort to get good at the math and understand cryptography and so on and so on, to understand what assumptions to make and in what context a scheme is secure, right? But implementing them, however, to me feels like it entails an unbounded scope of possible failure points and edge cases. And I stay as far away as I can from implementing cryptography because of this. So how do you still retain your sanity?
I think that's a bit of an assumption on your part, but
fair enough.
No, to answer the question. So firstly, I'm going to say that there's this like phrase, standing on the shoulders of giants, and S2M Big Number has done an enormous amount of work. Like I maybe underplayed it here, right? This is like 100,000 lines of assembler per architecture, 500,000 lines of proof per architecture. This is an enormous and like highly huge scope project. And so that has given me like a pretty stable base to do the high level things. I would say the level in terms of like complexity of S2M Big Num is variable. It goes from almost exactly what you need. You may have noticed on the key exchange performance that the key exchange performance of Graviola is exactly the same as AWS LCRS, and that's because it provides that operation as a whole operation. So you don't need to take parts and glue them together like you do with like RSA and ECDSA. So yeah, I think maybe I've not completely answered your question, but I'd say like this is a quite modest scope project in the sense that I'm taking something amazing and making it easy to use in Rust and filling in the gaps where the thing that is amazing is quite low level and not useful on its own. The other thing I want to say actually is there are lots and lots of cryptography implementations, and once you've studied lots of these for a while, you get a good idea of which ones you should go and read, and which ones you should go and read and point and laugh. Well, not point and laugh. That's really mean. But you know, which ones are good and which ones are bad. And you can learn a lot from studying other implementations. That's what I'm going to say.
I have a question. So for MLChem, I'm presuming that you would take the Jasmine implementation, right? So my question is, for all of this assembly code, how do you actually model the behavior, and how do you formally verify its properties?
Okay, so the first question, I actually plan to take the libcrux MLChem implementation. That is formally verified. Some fast paths of it, like they have an AVX2 implementation, which I think is still pending being formally verified. But like they are working on that, and it's the whole of like libcrux is a really interesting project if you're an enjoyer of formally verified cryptography in Rust. The other part, I think, is mostly a question about S2M Big Num. I'm not a great person to talk about that, but I can give you like a very poor description of what they do. So it's basically, they have some assembly and a proof. They have a instruction by instruction simulator for the semantics of those instructions. And then they have a big load of OCaml, which basically proves that once you've done all these instructions, that the inputs and outputs have this relationship, and the relationship is like these two numbers have been added together. So it's an equivalence proof, effectively, written in a high-level way and then a low-level way.
Time for one more question?
I think we have time for one more, yeah?
Okay. You had this great illuminating slide with all the crypto implementations and all the stars. And I noticed that you had more stars for Ring than for AWS LCRS. And still AWS LCRS is the default in Russell, so what gives?
Which column are you talking about? The assurance one, or?
No, like the total stars across all the columns.
Oh, right, okay. Can I refer back to that? Oh, there's lots of slides. I have far too many slides. Okay, I'm not going to get the slides back, but at least I can refer to it on my screen here. So I think AWS LC is kind of losing in this completely artificial evaluation, mostly through build simplicity, and the kind of reason for that is just its architecture. So it's a Rust binding to libcrypto or some derivation of libcrypto that comes from the AWS LC project. Ring is not that. It doesn't have that architecture. It's like fundamentally a Rust project which uses some limited parts of assembly and C from Boring SSL. So it doesn't like take the whole of Boring SSL, build it, and then start calling into it. And I think that has here we are. That has made it easier to make the build simplicity better. It's still not perfect. You still needed like a C compiler, but that is moderately easy for most users, I think. So yeah, did that answer the question? Thanks.
We have time for one short question. Hold on.
Oh, hello. So if I understand correctly, you use the STN big num as a underlying, and then you do the dynamic binding to the Rust, right?
Yeah.
And my question is, actually, I do a similar project, but my case is like a C++ binding, CXX. But I'm curious about why, do you have an opinion about rewriting this like a C++ library so that you can just like have one full Rust? Because I'm considering that. I know that the like underlying C and C++ library have a mathematical optimization embedded, but like could also rewrite everything in Rust, which makes actually more easy to like profile it by using like a one same tooling, because I'm having really trouble in terms of like memory profiling in my setup like C++ Rust.
Yeah.
So I'm curious about your opinion.
Well, I'd definitely be a proponent of like writing things in Rust first and then exposing them as necessary to like C and C++ users second. I think the other way is compromised in the fairly obvious way that you end up like going from a really nice language calling into a less nice language, whereas the other way you are writing an enormous amount of the whole problem in a nice language and then just dealing with the slightly more unsavory parts at the end. I don't know whether that answers your question. I think it's a generally good idea to. I would prefer to write things in Rust than consume a C or C++ library.
All right. Joe, thank you very much for your talk. I understood some of the words you said. I'm glad that you're in the ecosystem improving the security and safety of all of our code. Give it up for Joe.